In this example, we're going to do two more Lewis structures, which are a little more complicated than the one we did before. The first is CO2. CO2 has carbon, there's carbon, and oxygen, there's oxygen. Now carbon's in group 4A, that means it has 4 dots around it. Oxygen is in group 6A, that means it has 6 dots around it. There are 2 oxygens in CO2 though, so we got to have 2 oxygens here. Alright, so those are the elements I have to play with. Now the first thing we do is we look for the atom that has the most unpaired electrons. That's carbon. Carbon has 4 unpaired electrons, oxygen has only 2. So carbon is the central atom. We therefore will have to try and hang the oxygens off of the carbon. Now look, the carbon has 4 empty spaces. That's what those 4 squares are. Each of those empty spaces would like to accept an electron. I don't see how I can get 4 electrons into those 4 empty spaces, but I do see how I can get 2 electrons into 2 of them. Each of those oxygens can come up to the carbon and put 1 of their unpaired electrons into a space. Alright, that's what we have so far. None of these atoms have their ideal electron configuration yet. The oxygen has only 7 electrons, it wants 8, so I'll put little red squares indicating an empty space on the oxygen. The carbon has 6 electrons, it wants 8, so I'll put blue squares representing the empty spaces on the carbon. How do we get these atoms to each think they have 8 electrons? What we have to do is move the electrons around. Remember, an atom thinks it owns any electrons that appear between it and the next atom. So if I can get these electrons to move around a bit so that they appear in between the carbon and one of the oxygens, then things can happen. Look at the carbon and look at the oxygen that appears to its immediate right. Both of them have an electron sitting on top. I'm going to move those electrons down in between the carbon and the oxygen. Now look what happens. There are now 4 electrons between the carbon and the oxygen. Both the carbon and the oxygen think they own those electrons. Alright, let's do the same thing to the other 2 unpaired electrons. We'll move them in between the carbon and the oxygen right below it. Now there are 4 electrons between the carbon and that oxygen. Once again, both the carbon and the oxygen think they own those electrons. So look at what carbon thinks it owns. It thinks it owns all electrons either next to it or in between it and the next atom. So if I draw a square around all the electrons the carbon thinks it owns 8 electrons. Look at the oxygen. If I draw a square around all the electrons that the oxygen thinks it owns, it also thinks it owns 8 electrons. It owns 4 of them outright. 4 of them are between it and the carbon. So that's a total of 8. Let's look at the other oxygen. Once again, it owns 4 electrons outright, but it also thinks it owns those 4 between it and the carbon. So it thinks it has a total of 8 as well. So all of the atoms now have 8 electrons around them. They all satisfy the octet rule. Now remember, shared electrons are covalent bonds. When we have 1 pair of shared electrons, we represent that with 1 stick. When we have 2 pairs of shared electrons, we represent that with 2 sticks, and we call that a double bond. So in each case, we're going to take the 4 shared electrons and replace them with double bonds. So in this Lewis structure, the carbon is double bonded to 1 oxygen and double bonded to another oxygen. Now remember, there are many Lewis structures that are correct. You might have gotten this one, but you might have gotten this one. You also might have gotten this one. Now it turns out all 3 of those Lewis structures are equivalent. Now when we talk about shapes of molecules in Module 9, you'll find out that this one resembles the shape of the carbon dioxide molecule, but in terms of Lewis structures, as long as you have a central carbon double bonded to 2 separate oxygens, and each oxygen has 4 non-bonding electrons, then that's a valid Lewis structure for CO2. Okay, let's move on to the next molecule. The next molecule is HCN. Here's H, here's C, and here's N. Okay, hydrogen has 1 valence electron because it's in group 1A, carbon has 4 because it's in group 4A, and nitrogen has 5 because it's in group 5A. Now, once again, I have to look for the atom that has the most unpaired electrons. That's carbon. We'll put that in the center, and we'll hang the other atoms off that carbon. Now the carbon has 4 empty spaces. It wants to get 4 electrons to share those spaces. I don't see how I can get that to happen, but I can see how I can get 2 electrons to fill those spaces. Let's have the hydrogen move up and put its 1 unpaired electron in one of those spaces. And let's have the nitrogen move up and put 1 of its unpaired electrons in one of those spaces. Alright, that at least gets 2 electrons into 2 empty spaces on the carbon atom. We're far from done, however. Look, the carbon atom has 2 empty spaces still. The nitrogen atom also has 2 empty spaces. The only atom that has its ideal electron configuration is the hydrogen. It thinks it owns those 2 electrons in between it and the carbon, and hydrogen only wants 2 electrons, so it's satisfied, but the other 2 elements are not. How are we going to get those other 2 atoms to think they have 8 electrons around them? Well, let's look at those electrons that are on the top. I can move both those electrons so that they go in between the carbon and the nitrogen. This allows the carbon to think it owns them, and allows the nitrogen to think it owns them as well. I'll do the same thing for those bottom 2 electrons. I'll move them so that they appear in between the carbon and the nitrogen. Now look what I have. I have 6 electrons in between the carbon and the nitrogen. If I draw a square around all of the electrons that carbon thinks it owns 8 electrons. And if I draw a square around all the electrons nitrogen thinks it owns 8 electrons as well. So suddenly both the carbon and the nitrogen have their ideal electron configurations. Alright then, in this molecule, I have 2 shared electrons between the hydrogen and the carbon. That's a chemical bond, and I replace it with a stick. I have 6 shared electrons between the carbon and the nitrogen. That's a triple bond. It has 3 times as many electrons as a normal bond. So we call it a triple bond, and we replace it with 3 sticks. So this is the Lewis structure for HCN.